Okay, here's your follow-up video to the data collection that we did for the Forces lab out there with the AirTrack. And you can tell I'm doing this during break because I'm in my casual long sleeve shirt here. Okay, so let's take a look at what we got here. First, we are starting with our setup here where we're going to call this M1 and we'll call this M2. And in order to get through the theoretical calculations to figure out what should we expect the acceleration of this system to be, what we need to recognize is that, and I'm going to draw this is kind of our AirTrack. One of the assumptions we get to make is that our force of friction is 0 due to the use of the AirTrack. And so the only thing that is making this whole system go is what we're going to call FW2, which would be the weight of just this mass hanging over the edge. And we would calculate that by taking the mass of object number 2 and multiplying it by the acceleration due to gravity, which we know is 9.8 meters per second squared. Now, one of the things that I'll point out about, I'll call it signage here, is that when this thing goes down, this one goes to the right. So if someone asks about which way is positive or negative, because these are tied together with the string, there's kind of a dual thing here. Everything we are going to say is going to move in a positive direction, because this one moving down will be considered to be positive as this gets pulled to the right, because they do have to move together. So fortunately, we're not going to have to play this which way is positive, negative. Everything is going to be just moving in a positive direction here. And so that's why we will have our 9.8 here will be considered a positive 9.8. Now, one of the other assumptions up here that we're going to make use of, and this is based on, hopefully I did a good job with this, is that our initial velocity is 0 meters per second. And so if you watch the prior video and you're like, come on, Mr. Penovich, let the thing go. I was trying to get this butted all the way up right to where the photo gate was going to trip so that we could work with this assumption. And if there is any deviation from this, it would be really minor. Now the photo gates were set up at a known distance apart from each other, and that would represent our delta x, and that was 81 centimeters. And I went ahead and used the electronic balance to measure the masses of these two things, so I can tell you that M1, which was the cart on the AirTrack, is 284.62 grams, and M2, which was the hanging mass, is 20.44 grams. So what we need to calculate from this is the theoretical acceleration that we would expect from this system. And because of our assumption that the force of friction is 0, one of the consequences of that, because we're going to use Fnet equals m times a, and what we want to solve for is a, this Fnet, because we get to assume our frictional force is 0, simply becomes our FW2 calculation from up here. And the m, technically, because we have multiple objects that are moving together, we would refer to that as m sub cis, and the sub cis refers to the system, and this would simply be M1 plus M2. So using this equation, you can figure out what the theoretical, and I will add theoretical acceleration should be for the system. This is what we would expect it to be if everything came out perfect. So that's theoretical. Now, experimental. On the experimental side, what we did was we had 3 trials, and I'll call them number 1, number 2, number 3, and what we measured was a T initial, which was like the start time, and the T final, which was the end time. So what we would want to do, and I'm going to call this TI1, TF1, TI2, TF2, TI3, TF3. Now what we want, and I'll underline this to kind of show that that's like a header, what we want here is we just want a time, and we'll call it a delta t, which would be our, see, I'm not editing that out. You get to see all my burps and farts here. Is we are going to take our final time minus our initial time, so we will have what we call delta t1, delta t2, and delta t3. Once you calculate all of these, we want to, using those 3 values, calculate an average delta t. Now, once we have that number, we are going to use one of our values that we used on the theoretical side, because we know the delta x is 81 centimeters. And just like we assumed that I was careful in releasing this, we are going to assume that our VI was 0 meters per second, and then we have our t, which would be our delta t average value that would have come from our data collection. And what we want is we want to calculate an experimental acceleration, and we can do that using equation, I believe this is equation number 3, which is delta x equals 1/2 a t squared plus vi t. And our t is our value there. Our vi actually is 0, so that means that whole second term goes down to 0. And what we want to do is calculate that a based on this experimental data that we collected, and this is what we would call a experimental. Now, once you have finished doing that, the last step that you would go through would be to, first you would look and say, hey, is it close, is it not close? And the second thing is, to finish it off, is you would do a percent error calculation. Now, the beautiful thing that I would say about all of this is that you can process all of this on a single spreadsheet. So you could set up some cells to do the calculation to get your theoretical acceleration in one part of your spreadsheet, and then if you went over, you know, a few cells, you could set up all of the calculations that you would do for this to calculate your experimental acceleration, and then you, below that, you could have an area where you would just go ahead and calculate that percent error, and you would have everything presented there, and the spreadsheet would do all the calculating for you. If not, you could just use a blank piece of paper and kind of sequester things in certain areas. So you have the theoretical side, the experimental side, and then again at the bottom, everything, these kind of come together in calculating the percent error. So that's the theory behind it. This is what we actually measured. I'm going to leave it up to you if you want to process this. I will be processing this as well. So if you go ahead and do this and you want to ask, what did you come up with, Mr. Penovich? we should come up with similar results because we are using all of the same numbers here. So since I'm posting this during break, I will say I hope you're having a good break, and feel free to reach out to me if you want. I'll check my email if you have any questions about this, and we'll either hear from you over break or see you after break. So take care. Thanks.